Actually, in physics, in the physics community, if there's like a couple that doesn't ever get along, they're always fighting about everything, we call them a third law pair. You know, those two guys, I don't want to go out with them. They're a total third law pair. They'll fight all night. But there's so few couples it hardly ever comes up. So if you ask anybody about that, they'll say, I've never heard that before. But it happened once. So now let's do two masses on a frictionless table. Okay. And now we want to be more real. Okay, we want to keep this like legit, normal, real world stuff. So here's the frictionless table, so we'll pretend it's ice. And I'm going to make them both like peanuts, like this. There we go. So this peanut here, oh, I'm going to regret this, is going this way. And this peanut here is going that way. And it's the same thing. Then they're going to react with each other. They're going to hit. And they're not going to break open or anything. Right, they're sliding along, and they're going to bounce back. But they're on a frictionless table. So now, let's do the FBD of these nuts here. FBD of these two things here. Sorry, a 14-year-old writes my material, so F21. So we have the force of nut 2 on nut 1, F21, right? But we also have mg pulling it down. Wait a minute. Okay, well, that's cool. M1g, we have the normal force on 1. There's the FBD, and they're legumes, I know. Okay, just let me have my fun. How do you know if the objects bounce off of each other? What if they stick together and move in the same direction? Just wait 30 minutes. If you can hold on for 30 minutes, we're going to talk about that. But right now, everything we're talking about bounces off of each other. But when they stick together, they still have an action-reaction pair. It'd be harder to draw. Okay, so that was number 1. Here we go, number 2. It feels F1, 2, right? The force of 1 on 2. It also feels M2G, and it feels N2. So it's more complicated, right? Let's see. So the action-reaction pairs, if I try to draw, you know, this around it, do I have an isolated system? Well, in the x direction, check. It's isolated. Because look at those x forces. The only x forces we have are an action-reaction pair. Let's look in the y direction. Okay, now we have a problem. So do we have, if I draw the dotted line like that, do we have an action-reaction pair in the y? No, we don't. Hopefully you remember from third law, the normal force and the weight are not an action-reaction pair. So if we wanted to make a system, the system in the y to be isolated, we'd have to put in the Earth, the entire Earth. Oh my God, the system just got big. And we'd have to put in the table that's holding these nuts, right? And then the thing would have to go all around the entire Earth, like that. And that would be really stupid, right? Then every stupid isolated pair we draw of something on the Earth would have to include the whole Earth. Nobody wants to do that, right? So what you do is that's what the parenthetical statement is about. So why? Here the answer is no. You would need the Earth and the table. Right, because the table has the action-reaction pair for this normal force, and the Earth is for the weight. So what you would do, what you can do in the real world of solving physics problems is for the dimensions you care about. Dimensions you care about. I mean, you care about your grade. For the dimensions that impact your grade that you care about. Okay? I don't know if you really care about the horizontal dimension or not. That's more of a philosophical question. Okay. Okay, let's see. So when you do a 1D problem, sometimes you'll see a book where we're really obsessed with this and draw the Earth in the system. Sometimes you'll see, well, they just did that 1D problem. Where'd the Earth go? This is the reason. It only doesn't matter for each one. Okay. So now we're getting close to doing some problems. Good. Okay. All right.